Howdy folks, Matt right back here and talk to you about another way to find a potential. Last time we talked about conjuring up solutions by doing the method of images. This time what we're going to do is we are going to find the potential by solving the Laplace equation exactly. So what we're going to do is we're going to look at a variety of different scenarios. So in this scenario, I have three plates. I have a plate that starts at z equals a, and it covers everywhere, all the way out to infinity. And then I have another plate, which is at z equals 0, and that goes everywhere. And then I have a plate, a third plate, that nicely goes from z equals 0 to z equals a. And it's at a voltage of V, right? It's a function of voltage, and it sits here at x equals 0, right? So if I'm looking at this head on, this is what I see. Well, I see that as x goes this way, my potential is equal to 0, and here it's equal to 0. And here, my z goes up, starting here at 0 and going to a. And the voltage there is going to be V. And I know that there is no charge in the inside. Well, that's great, because that tells me that the Poisson's equation, or the charge density, is 0 inside, and that all I have to do is solve Laplace's equation for where there's no charge density and match these boundary conditions to my solution, and I'm in business, which is pretty amazing, right? All right, let's do it. So we start with Laplace's equation on V equals 0. And I'm only going to do this in 2 dimensions because the thing that's happening in the y direction here, sorry, this is y equals 0. The thing that's happening in the x direction here is just, it's happening for forever. So I'm just not even going to think about it. I'm just going to look at the y in the z direction and say that thing is completely symmetric in the z direction, in the x direction, sorry. So this is going to be the partial with respect to y squared plus the partial with respect to z squared. Now there is a partial with respect to x squared, but because we expect v to be completely uniform in that direction, non-changing because of the perfect symmetry, that term will go to 0, right? Just make it go to 0. So we are going to use a method called separation of variables. Okay, it's a trick, and it makes me happy. All right, so what we're going to do is we're going to say that v is equal to xy, right? Sorry, v is a function of xy, and we're going to call that equal to 2 functions. M, which is only a function of x, and n, which is only a function of y. Now remember what we talked about before. It doesn't matter how we find the solution, as long as we find it, and it matches boundary conditions. So this jump may seem a little extreme, right? Like, is there any crossing, right? But it doesn't matter, because if it's a solution, and it matches the boundary conditions, then no matter how we came up with it, it's a valid solution. So this is a valid thing to do. Okay, so what we're going to do is we're going to plug that in for v. So we have 0, sorry, not xy. I'm confusing myself already. yz, y, and z. Right, so I get, and now I have mn plus Now here, m is a function of y, and n is a function of z. And if I look at this partial, I'm only taking the partial with respect to y. So this term, this n term, is going to be a constant because it is only a function of z. So I can pull it out of that partial derivative. N. And I can do the exact opposite thing here. Because here I'm taking the partial with respect to z, and I know that n has a function dependence of z, but y depends on y. Sorry, m depends on y. So I'm going to go ahead and keep the n term in there, and I'm going to pull out the m. All right, then I'm going to do something wacky. Right, this is equal to 0, and I'm going to divide by nm. So these n's are going to go away, right? This term is just 0 because 0 divided by anything is just 0. And here the m's are going to go away. So I get the following. 0 is equal to 1 over m dy squared m plus 1 over n ddz squared n. And I can even bring one of these over to the other side of the equation, right? So let's do that. Let's bring this on the other side. So I get minus 1 over n ddz squared n is equal to 1 over m Okay, now take a moment and look at that. This is super duper amazing, exciting. I can't believe it's not butter. Oh my gosh, this is amazing. Everything on the left side only depends on one coordinate, the z coordinate, right? N only depends on z. Z only depends on z. So everything here depends on one coordinate, z. And everything on the right side is only depending on one coordinate. That coordinate is y. So it doesn't matter what point I'm at on here for for z or y. Doesn't matter what I put into this equation, I should get the same thing, right? They should be equal. So the only way that could be is if this term here and this term were constants. That we had the constant over here is equal to the constant over there. That does not change. Because it doesn't change no matter what value of z you put in or what value of y you put in. Because any value here has got to give you k squared. Any value here has got to give you k squared, right? So any point got to give you k squared. Now why did I choose k squared and not k? It's because I have some hindsight. I know where we're going, right? When you're solving this for real, you may not know where you're going and you might just use k. But I know we're going to an amazing place. So I'm going to go ahead and use the k squared just because I know we're going someplace interesting. Hold your horses. Okay. Woo! My gosh. Now we have, instead of one giant differential equation, now we have two smaller differential equations. So let's start with the y differential equation. So we have 1 over m equals k squared. So what we'll do is we'll multiply both sides by m, and we get the second derivative of m is equal to k squared times m. So, there are so many wonderful ways to solve this problem. But I like to guess, right? What thing, if I take its second derivative, gives me back itself, right? So what thing gives me back itself if I take the first derivative? Well, isn't that the e? Right, so if I have ek y, and I take the derivative of that, I get k eky. So what happens if I had taken the second derivative? Well, I take the first derivative, and then I take another derivative. Wait a minute, if I take the second derivative of this function, it gives me back k squared times that function. Isn't that exactly what I got here? I'm taking the second derivative of m equals k squared times the function. So m of y is going to be equal to a, some constant I don't know yet, e to the ky. But it's not enough. Why could that be? Second order differential equation means if I were doing traditional methods and I had to integrate, I would integrate not once, but twice. And each time I integrate, I get a plus c. But if it's some constant I don't know, I got to figure crap out. So if I had to integrate twice in a second order differential equation, I should have two constants. But I only have one constant. So I need another solution to be able to describe the goings-on with this differential equation. So yeah, I need another orthogonal term that I can use. And so if I think about it here, I can say, well, what is the pair to e to the kx that is going to work? And it is just going to be plus b e to the minus ky. Let's test this. I take the first derivative, e to the minus ky, it gives me minus k e to the minus ky, taking the derivative, and then I take the derivative again, and it gives me minus k times minus k e to the minus ky, but minus k times minus k is just k squared. So that is also going to be a solution. So now I have m as a function of y that matches this differential equation. And I have another side to go. But let's just record this. So we know that m of y right? We know what those are. Okay, let's look at the other side. All right, here now I have the second derivative with respect to z of n equals minus k squared n. So it's almost identical, only there's this pesky little minus sign. So what function do I take the derivative of twice, and it gives me back my function, but gives me a negative sign? Well, there's a couple I can think of. E to the I kz, that works. How about cosine kz? That works, right? Well, the derivative of cosine is minus sine. Derivative of minus sine is minus cosine, which is actually gives you that alternating pattern that you need. So which one am I going to use? In hindsight, I'm going to use cosine of kz. But you could use e to the I kz, and there will definitely be times when we use that. So let's not use this. Let's use this. We can take the second derivative of this, and we find we get minus k squared cosine kz, which is a valid solution to that differential equation. Again, there's only one constant, so so we used a and b there as constants, so let's use some other constants here. Let's use d cosine kz. And again, for the same reason, you need two valid solutions in order to solve this differential equation. We only have one. So there's a couple different ways we can do this, but you know, it's just nice to pick the orthogonal solution, which is sine kz. So then that gives me two solutions. Okay, now let's start applying boundary conditions. All right. Okay, step one. We are going to look at the following scenario. We're going to look when z is equal to 0. We're going to look for when z is equal to 0. Well, I know that v is going to equal 0, and I know that v is m times n, right? So one way that that could be equal to 0 for all values of z would be if this term here, the n term, was equal to 0, right? So I know that n of 0 has to equal 0. Now, the n term could equal 0, but it would only equal 0 for one value of y, right? And we want it to be equal to 0 for all values of z, right? So we want to use the function here that's a function of z. So I can now plug in to see what my constants are in my differential equation. So I have d cosine k times 0 plus e times the sine of k times 0. Well, the sine of 0 is just 0. So I know that that tells me that the cosine of 0 is 1. And that leads me to the conclusion that d is equal to 0. Sweet! That eliminates some of the stuff that I don't know. D is going to be equal to 0. So now, I only have one more thing to worry about. One more constant in that equation. All right? Now let's look at another boundary. Let's look at here. When I know that y equals 0, right? So y starts here at 0 and goes to infinity. So when y equals 0, I know that this term has to be v, right? I know that the, well, let's wait on that. So, crap, got ahead of myself here. All right, let's not look at that one, because that one's off topic. Let's look at the situation when y goes to infinity. So if I'm here and I'm infinitely far away, you can only hear me now, but I'm infinitely far away from this voltage plate here. So I'm infinitely far away, then I would expect that m would also go to 0. Because I'm infinitely far away from that, the effect that I'm going to get from that is going to diminish all the way to 0. So if I look at this and I say m as y goes to infinity is going to be a e to the infinity, right? plus b e to the minus infinity, well, this term here is going to have no problem. It's going to go to 0. But this term here, it's going to go to infinity. So the only way we can make this term 0, right, is if a is 0. So that tells me the following. That the m has got to be b times e to the minus ky. All right, we're about halfway done through the boundary conditions. But now I want to take a moment and go back. I hid something under the rug. Tricked you. So when I pulled the n term over to this side of the equation, I could have put the minus sign here, or I could have put the minus sign there. I had a choice. Did it fit on the z or did it fit on the y equation? And I snuck it in on the z equation because I saw something. I didn't tell you about it. I just kept going. But we should go back and think about it. Why did I choose the negative here and not here? Looking at my physical picture, here the voltage is 0. Here the voltage is 0. I had an instinct that my solution, that I wanted something whose second derivative came back in on itself so that it would give me something that was oscillatory. Something where I could start at 0 and end at 0. And sure enough, the end differential equation gave me the sine function. On the flip side, when I had the positive differential equation here, it gave me something whose second derivative is positive. So something that's going to exponentially increase or exponentially decrease. And that made sense because in the y direction, this was going to go on forever. So I kind of was thinking, give me something that has a solution that doesn't come back in on itself. It has a nice behavior that goes on for forever. So I had a choice. I could have chosen the negative here and the positive here. Now, if I did it backwards, would it have worked out? Yes. But it can get uncomfortable. And you might not lead to an easy solution. So it takes, sometimes you can take a moment and think through the geometry of the problem you're trying to solve to try to figure out where to put the minus sign in a problem. Where can I take a trick in the geometry to help me make my solution easier to deal with? Okay, so now the potential, so now we know what the potential is, right, of y and z is equal to m of y, n of z, and that's going to be b times e to the minus ky times e sine kz. But b and e are both unknown constants. And one unknown constant times another unknown constant is going to give me, an unknown constant. So let's reduce this down to f e to the minus ky times sine kz. Okay, let's apply the next boundary condition. Let's now apply this boundary condition. When z equals a, right, the potential is equal to 0. Okay, so that tells me that the following must be true. All right, now, if f were to equal 0, that would work, but now I would have a trivial solution. It would be 0 everywhere, right? Because there's only one unknown constant here. So, and I know that there's a voltage here, so that can't be the case. So I can't make f equal to 0. E to the minus ky, I might be able to make this 0 for one value of y, but it's not going to be true for all values of y. And I need something that's going to be true, not just here, but every point all the way up to there. So I can't really work with that. But I could take this sine of Ka and I could make that 0, right? How so? Well, the sine of Ka is equal to 0 when Ka is equal to n pi, right? Where n is any number from 1, 2, 3, all the way up to infinity. And I have to include them all. So now my solution becomes solving now for k. K is equal to n pi over a. It becomes equal to the sum, n equal 1 to infinity, of fn exp, right? That's just exp of x is equal to e to the x. So, and writing it, now I have a function which includes every value of n, right? Every possibility. And it's going to add up to what my solution is going to be. So now my solution has gotten even more complicated. I have an infinite number of terms in an expansion, and I got to include all of those terms in order to make it work. That's a lot. So what do we do next? We have our final boundary condition. We know that when y equals 0, v equals v. Okay, so good. Let's plug it in. So I have v equals the sum n equal 1 to infinity, fn. Now I'm going to have e to the 0, right? Because I'm plugging in 0 here for y, times the sine of n pi z over a. Of course, e to the 0 is 1. And this becomes n equal 1 to infinity, fn sine n pi z. And then you're thinking like, you're telling me I have a constant equal to a sum of terms, divided by a, of course, equal to the sum of terms with some function which is orthogonal and complete. Maybe it's the function of sine. What can I use to find out what those constants are? And your brain should be sending signals every which way and going nuts, and you should be jumping up and down and being really happy because this looks a lot like, you got it, Fourier series, right? So we can use the Fourier trick in order to find out what those constants are. All right, so how do I determine what those are? Oh man, this is great stuff. Okay, so I'm going to multiply both sides by some factor sine m pi z over a dz, and we're going to do this through the whole cycle from 0 to a. It's going to be equal to the sum of n equal 1, infinity, Fn. And now, we got to do the same on this side of the equation. And we're going to go around one cycle. And this is fantastic, right? We know what that is, right? It's half the cycle, so it's a over 2 times the delta nm, right? Means it's 1 when n and m are equal, and 0 when they're not, times Fn. Okay, now, how do I know this? Well, you can always do a trig identity, or you could do something like plugging in for the sine of x is equal to e to the ix minus e to the minus ix over 2I, right? And you can plug that in for both of them, expand them, and then do the integral, and it nicely comes out to this. Right? And now this is an integral that I can do. I get v, I get an a over m pi, and then I get a cosine pi mz over a from 0 to a. Okay, and it's negative, right? So how does the right side give me Fn? Well, let's think about it. So let's say that m was 6, right? So I pull out my a over 2, and now I have my sum, which is going to be F1 times delta 1, 6 plus F2 delta 2, 6 plus F3 delta 3, 6 plus F4 delta 4, 6 plus F5 delta 5, 6 plus F6 delta 6, 6 plus F7 delta 7, 6 and whatever, all of those terms. I know that this delta is only equal to one of two numbers. It's only equal to 1 or 0, depending on the arrangement of these indices. So if I have delta nm, it's equal to 1 when n equals m, and 0 when n doesn't equal m. So if I look at this thing here, delta 1, 6, is 1 and 6 equal? No, this is 0. How about here? 2 and 6 equal? No. 3 and 6? No. 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 7 and 6? No. What about 6, 6? For 6, 6, they're equal. So that tells me that I'm going to have a bunch of zeros and one term, f of 6. So this is going to be equal to a over 2 f6. Now, of course, we had assumed that m equals 6 here. In practice, we're going to say that we're really looking at the mth term, right? So then if you look here, you have fm, a over 2, it's equal to minus v, a over m pi. And here you're going to have the cosine of a, which is going to be the cosine of m pi minus the cosine of 0. The a's cancel. You get fm. So there's going to be, you get minus 2v over m pi, now times this, the cosine of m pi minus the cosine of 0. Okay, so the cosine of m pi, right, it's either going to be even or odd. So the cosine of pi is what? It is going to be, that's right, -1. The cosine of 2 pi is +1. Cosine of 3 pi is -1. And they alternate back and forth like that. So when m is even, well, what's the cosine of 0? Cosine of 0 is 1. So when n is even here, you're going to have terms that are going to cancel out, right? You're going to get +1, -1, they're going to go away. So the only time when they won't go away is when n is odd. And in that situation, you're going to get -1 times our -1, which is -2. So then your Fm is going to be plus 4v over m pi. So remember that v, yz, is equal to the sum of n, equal 1 to infinity, Fn, right, exp minus, so k, which is going to be n pi y over a times the sine of n pi z over a. And now I know what f is. This is going to be, when even, it's going to be 0. And when odd, right, you have a -1 minus -1 gives you -2. It's going to be 4v m pi. So this reduces this down to n odd the final solution. Sorry, it's n, right? And that gives me a complete analytical solution. Now you might say, well, wait a minute. You still have a sum of infinite terms. And you're right, you do, but it goes off as 1 over n. So the higher you go up with n, the effect of the term is going to diminish. And so the more terms you include, the more you're going to approximate what the actual potential is.